Hello everybody, and today we're going to get into part 2 of this video. So in part 1 of looking at the moving data, we drew a graph and we did the residual analysis. So this is what we did in part 1 of this video. Please see that if you'd like to look at the residual analysis. What I'm going to do right now is look at a couple of pieces of this regression analysis that would be pretty important to us. First of all, we have the equation that would be important. What is the prediction equation? To find residuals, you need to know the prediction equation. Well, the y-hat, the prediction equation, is given in this chart. Again, if you're not sure where this chart came from, please see my prior video. I'm not going to talk about that anymore. So what we have, 2.3697, 3697. So there is my prediction equation, given to us by this nice chart, or if you did the residual analysis, given to us in this chart right there, your choice of finding it. More details here if you want more data, that is more decimals of accuracy, or if this is good enough for you. So there's my equation. So the first thing I notice is it has a slope. 0.05 is the slope. And so obviously the first thing is, what the heck does this slope represent? What does slope represent? Well, yes, we got the math answer. Change in y over change in x. It is the rise over the run. But let's look at this in terms of the application. What are we looking at? Y, x. We're looking at the change, the average change in hours per one change in cubic feet. That's what this represents. This would be the average change in y, which in this case is hours, labor hours, based on a 1 unit change in x, which is the cubic feet moved. So what we have here, and allow me to shrink down a little bit so you can see it, is the 0.05 represents the average change in hours based on a 1 unit change in cubic feet. If you can't read something, you always do merge and center, and you'll be able to read it clear. So 0.05 average change in hours based on a 1 unit change in x cubic feet. Kind of tells you again, per cubic feet, how much longer it's going to take. If we go to an apartment that has 1 more cubic foot, how much more time and hours would we need? All right, Y-intercept. Well, the Y-intercept, in most times, it's not a useful value, but it is, as we call it, the classic 0 point. That is, if we had x is 0. So if we had x is 0, because think about it, if you plugged it into your prediction equation, or over here, if you plug in 0, what do you get? You get negative 2.3697. And so that's the Y-intercept. So what is this? This is if x, which in this case x is cubic feet, is 0. So that's how long it would take. We've got a lot of equals here, and of course Excel doesn't like equals. Excel is not liking the equals. They're thinking we're writing an equation, and so it's not happy with me, trying to make Excel think it's just a comment. There. So negative 2.3697 is the amount of that would be the actual labor hours if cubic feet is 0. So that would probably be the better way of saying it. It would take negative 2.3 hours for 0 cubic feet. And again, most of the time that sentence does not make a heck of a sense. And it doesn't in this case. We're not moving anything. It shouldn't take you any time. You shouldn't be getting time back on your life, but probably should be more of a 0-0. Alrighty, move on. Next question, r squared. Good news, right there it is, 88.92. And I'm going to write it as a percent, because typically the coefficient of determination is usually a percent. So 88.92%. So what does it mean? Well, to me, it's a very, very important variable. This is how much you know of the relationship between x and y. What do I mean by that? Well, what I mean by that is 88% of the reason why which in this case is hours, varies. So what is the biggest reason the number of hours it takes to move all the boxes in and out of a popper? What is the number one reason? We happen to have it here. 88% of the reason. That's the number one reason that hours varies is due to the variation in X, which again is cubic feet moved. I like to have the biggest reason sitting in front of me. I like to know right in front of me, I have the, no, I don't want that. Merging these guys. There we go. Got to merge the right areas so I can read it carefully. So I know the number one reason labor hours will fluctuate because of the fluctuations in cubic feet. Excellent. Now there are other variables we're going to use later in multiple regression. They may increase this value, but the question is it worth it to increase it up to any more than 88%? That's a pretty darn good coefficient determination. All right, let's move on. Question E. Question E is predict. Of course, you have a prediction equation right there. You can easily make a prediction. All you got to do is tell me what would you like to plug in. Oh, you want to plug in 700? Then I will evaluate that 700 and allow me to, I'm using rough numbers there. It's actually 0.0501. If you notice, yes, that is acceptable. In my equation, I use 0.5. Let me go up there and go 0.1 because that's what Excel actually gave, right? It gave 0.501 X. Well, X in this case is prediction. You do got to know the difference between your X and Y, all right? X is cubic feet. So this is 700 cubic feet, and that's why I'm plugging 700 in. So my prediction would be 32 labor hours, 32.7 labor hours. So if somebody called up and said, hey, I got 700 cubic feet of boxes to move, how long is it going to take? I can easily tell them it's going to take me predicted 32.7 hours. And since I charge hours per hour, this is going to be your cost. Now, in most times, we do want to take a look at some of our variables and build confidence intervals, because there could be times you might want to change values in your predicting equation to higher and lower values. So the value to me that's the most important is that slope number. And so in having a confidence interval, a lower bound and an upper bound for the confidence interval of how big and how small the slope could get, because remember, this data is sample data. I'm assuming we just pulled sample data out of here. If this was actually population data, we'd be speaking a totally different language right now. But I'm believing we have a sample data set. Most of the times we collect a sample. And since we have a sample data set, this would be a sample slope. The 0.0501 would be a sample slope. So that means there is some variability. Let me go to the residual box, the residual chart. What we have over here, nicely built for me, so I don't have to do much, is the 95% confidence interval. So I see the lower bound is 0.04 and the upper bound is, let me do 3 decimals, 0.044. Get some accuracy here. The lower bound is 0.044 and the upper bound is 0.056. And that's important to me. It tells me on the low bound, if I collected data, I am 95% confident in the true slope, the actual beta, all right, the actual beta 1 would be a number between 0.0044 and 0.0056. Where is it between there? I don't know, but I'm 95% confident that the true slope is between those two numbers. Now, this is not the true slope again. This is the sample slope. This would be the American letter B1. Beta 1 is what I'm talking about. The true slope, beta 1, is some number between them with 95% confidence. There is a 5% chance I am wrong. So what I notice is if for some reason I would like to change my prediction equation, so my equation predicts a little lower, I can remove this sample slope with a lower bound if so choose. Or if I want to, say I'm going into good economic times, I want to replace this slope with a higher slope, we could do it with that. You might be saying that might not mean much. The answer is it could mean a lot if we're dealing with hundreds or thousands of cubic feet. It could really amplify our hours if we change it to one of these. Alrighty. Often we like to test the slope. We like to see if the slope is significant. So what we do is we do this hypothesis test. We do the no, the slope is 0. That is, we don't believe the slope is actually relevant. But our alternative is, if there's significant enough evidence, we will state beta 1 is not 0 and there is a significant slope. So how does one calculate out the t-test for the slope? How does one actually calculate out the t-value and the p-value for this? The good news, A, you could check your stats book and do it by hand, or, once again, in the residual analysis, you get them for free. And you should verify that those are actually the numbers. They are, but you should verify to make sure you can build them. Same thing with the confidence interval for slope. You should verify these numbers the first time you do them so you know the equations make sense for building the confidence interval or for running the t-test and p-value. So our t-statistic is 16.52. That is our t-statistic, 16.52. Well, the t-statistic is roughly a normal curve, right? Remember, the t-curve is roughly normal based on degrees of freedom. And that t-statistic is well outside of the 2s and 3s, the plus and minus 2s and the plus and minus 3s. So this is a highly significant variable. And so that also makes sense when we look at the p-value. The p-value here, E negative 18. This means we are highly, our p-value is 0. That means we're highly significant. Remember, a low p-value means we're highly significant. And in this case, that means we have to reject, right? If your p-value is less than alpha, then you would reject. What's your alpha? I don't care what our alpha is in this case. Our p-value is 0. Typically, your alpha is 10%, 5%, and 1%. Your p-value is less than pretty much any alpha. What does that mean? In the end, we reject H naught. We reject the no, which means we agree that beta 1 is not 0. We truly agree that there is a significant slope here. So when somebody says, do you have a significant linear relationship? I can say yes, because of part F. And since 0 is not in the 95% CI, and yes, because of part G and my t-test. Let me just mention quickly why I stated this little fact here. Why does it matter that 0 is not in this confidence interval? Well, let's think about this. If my actual true slope could have been 0, if 0 was in this interval, and that means there's a chance that beta was 0, what could that mean for the prediction line? Well, that could mean your prediction line was flat. And think about that. If your prediction line could have been flat, that means as cubic feet increases, ours does not fluctuate. What that means is they're really not related. All right. If you get a horizontal prediction line, you really are looking at two variables that are not related. We don't have that in this case, I want to repeat, because 0 is not in this interval. And I reject it, and beta 1 is non-zero. So both of these facts show me that I truly have a significant linear relationship. I thank you guys for watching part 2 of my video on regression analysis.